The crane lifts slowly, steel cables tighten, and below them, suspended in a translucent mesh harness, the giant squid begins to rise. Not like a fish, but like a monument emerging from the ocean. Its arms, still supple and heavy with seawater, sway gently in the air, each movement a reminder. This isn't just seafood. This is one of the most fragile biological structures ever handled by industrial logistics. In Japan, transporting a giant squid isn't a routine. It's a marine engineering exercise. One mistake, and the animal liquefies from the inside out. At full maturity, a Dosidicus gigas can weigh up to 500 kilograms. But weight is only part of the challenge. Unlike most fish, squids have no bones, no rigid skeleton to stabilize them. Their bodies are soft-mass hydrostatic structures, supported by internal pressure rather than rigid frames. That makes them biomechanically unstable, a living jelly column more than a compact cargo. Try to lift it like a tuna, and you'll rupture it. Try to pack it in ice, and you'll break it down on a cellular level. For Japanese operators, this means one thing: precision, not force, is the only way forward. The process draws parallels from an unlikely field: offshore oil. In naval engineering, deep-sea risers are long, flexible pipes that must be lifted without kinking, bending, or snapping. The techniques used to hoist them, using synchronized tension, dynamic buoyancy, and vibration-damping rigs, have inspired the very systems now used in Japan's high-value squid harvests. The same principles that stabilize a kilometer-long oil pipeline are being repurposed to lift a creature that can disintegrate under its own weight if mishandled. But even after the lift, the race has just begun. A giant squid's internal chemistry begins to degrade rapidly upon capture. Its tissues are rich in ammonia, a compound that helps it control buoyancy at depth, but becomes toxic and destabilizing at surface temperature. Enzymatic reactions start almost immediately, breaking down proteins in a chain reaction that, if not interrupted, leads to liquefaction. In less than 45 minutes, a squid can lose all structural integrity, not spoil, collapse. To counter that, Japanese processors employ a thermal strategy that's as much science as logistics. Instead of dropping the squid into conventional ice baths, they use layered ice brining systems. These systems circulate ultra-cold saline around the squid in precise gradients, cooling the body without inducing what's known as thermal shock. A sudden temperature drop, like in flash freezing, causes the squid's tissues to rupture internally. The brine technique slows the descent, drawing heat out in a controlled spiral, like a spacecraft re-entering Earth's atmosphere. Not too fast, not too slow. When seen from above, the operation is almost surreal. A soft-bodied leviathan suspended in engineered stillness, surrounded by a network of machines tuned not for power, but for gentleness. On one screen, a technician monitors thermal curves. On another, a schematic shows pressure distribution on the lifting mesh. Nearby, a digital overlay compares the stress profile of the squid's body with that of a flexible oil riser 1 to 200 meters below the sea. This isn't food logistics. This is soft body physics applied at an industrial scale. And yet, it's happening quietly. Night after night, in ports along Japan's rugged coastlines, these operations unfold away from public view. Invisible, delicate, essential. You realize that behind every plate of grilled Ika, there's a choreography of mechanical precision and biological urgency. Behind every shipment, a race against decay. And behind every giant squid that reaches the table intact, a fusion of marine biology, logistics, and offshore engineering, all working in synchrony to do the impossible, transport the untransportable, preserve what was never meant to survive the surface. At first glance, a squid appears docile once it leaves the ocean, motionless, compliant, heavy with seawater. But that stillness is deceptive. Beneath the surface, its body is fighting a silent collapse. Unlike most marine cargo, squid are not built to withstand gravity. They are ocean-dwelling soft bodies, evolved to float, not to lie still in crates. Without the natural buoyancy of salt water, their own weight becomes their worst enemy. As they settle into standard containers, they begin to deform, slowly, invisibly, until the internal pressure bursts their tissues from the inside. This failure isn't visible at first. No broken bones, no bleeding, no cracks. Only a loss of structure, as if the body were folding inward. Scientists call it deformation under inertial load, a phenomenon where soft tissues collapse when subjected to forces they were never designed to bear. The very act of placing a squid on a flat surface triggers this process. Conventional fish crates, designed for denser, more rigid species, only accelerate the damage. The moment the truck begins to move, each vibration, each bump in the road, adds micro-trauma to the creature's gelatinous frame. In response, Japanese engineers turned to a source of inspiration rarely associated with the fishing industry: jellyfish aquaculture. For decades, specialized tanks were developed to suspend jellyfish in simulated zero gravity, circulating water in controlled loops to prevent the animals from sinking or touching the sides. This same principle has now been adapted to squid transport. Using hydrodynamic suspension tanks, the squid is kept afloat during transit, as if still adrift in open sea. Gentle currents move through the chamber, keeping the body suspended, while shock-absorbing materials insulate it from external vibration. The physics behind this design is precise. While a tuna can withstand transportation forces of up to 8 G, the equivalent of 8 times the force of gravity, squid tissues begin to rupture beyond 1.5 G. That margin is narrow. It means that squid require kinetic damping systems typically used in aerospace packaging or medical equipment. Technologies that prevent sudden acceleration, isolate shock, and stabilize pressure over time. In a way, transporting a squid safely is more like shipping a satellite component or a biological sample than a piece of food. In Okinawa, one cold chain facility made a radical change. They retrofitted their transport units with these suspension tanks, equipped with ocean current simulators and continuous water flow buffers. Over the course of a single harvest season, carcass loss dropped by 72%. It wasn't the ice that preserved the squid. It was motion, or rather, the careful simulation of its absence. The squid didn't travel as cargo. It traveled as if it were still in the sea. All of this raises an uncomfortable but revealing question. What if transporting a squid demands the same delicacy, planning, and preservation strategy as shipping a live human organ? When a human heart is moved between hospitals, it is never simply packed in ice and placed on a plane. It is monitored, isolated from vibration, and kept in a thermal and kinetic cocoon designed for continuity of structure. The squid, too, is a body that cannot afford collapse. Not because of its value, but because of its nature. This is not logistics in the conventional sense. This is bio-integrated transport, a mode of thinking where the cargo shapes the vehicle, not the other way around, where engineering bends to biology, and where the silent stress of a creature without bones becomes the driving force behind the design of a new generation of transport systems. A squid, after all, is not a box of goods. It is a column of moving water trying to stay intact in a world of angles, breaks, and roads. Preserving a giant squid is not just a matter of temperature. It is a matter of timing, chemistry, and molecular choreography. From the moment the animal is removed from the ocean, a silent transformation begins inside its body. Unlike many fish that undergo a rapid drop in pH after death, slowing enzymatic activity and preserving muscle, squid experience a delayed post-mortem acidification. This delay allows proteolytic enzymes to remain active longer, accelerating tissue degradation. If cooling is too aggressive, it doesn't stop the process. It triggers an internal collapse. When squid are flash frozen or chilled too quickly, the cells undergo a phenomenon similar to thermal shock in metals. The outer layers contract, the inner tissues resist, and the result is microscopic tearing. But unlike steel, squid muscle doesn't crack, it melts. Its texture breaks down into a gelatinous form, making it useless not just for export, but even for local consumption. The boundary between preservation and destruction is thinner than in almost any other seafood category. In this context, cold can be a tool or a sabotage. That's why Japanese exporters no longer rely on conventional refrigeration. Instead, they employ phase change materials, or PCMs, that release cold gradually. These materials are engineered to maintain specific thermal plateaus during melting, ensuring that the squid is cooled at a rate slower than 1.5 degrees Celsius per hour. This method, known as time-diffused chilling, avoids internal stress while preserving enzymatic integrity. The process is less about freezing and more about guiding the animal into stasis, not by stopping time, but by stretching it. A logistics lab in Kyoto tracked this method over 6 months. Their results were striking. Squid cooled with a 0.8 degrees hour gradient retained their muscular texture and brightness nearly 3 times longer than those subjected to deep freeze chambers. Where flash-frozen squid became dull and flaccid within 72 hours, those transported with diffused chilling retained structural cohesion for more than a week. It wasn't just about temperature, it was about respecting the biology of a body not meant to be preserved in pieces. In the bays around Tokyo, a network of exporters has adopted these methods not just for elite markets, but for bulk shipments as well. One operation applied sushi-grade thermal protocols, adapted from techniques used in bluefin tuna handling. Over a trial period of 9 months, spoilage losses decreased by 38%, while consumer feedback reported a noticeable increase in texture quality. These results aren't accidental. They are the outcome of treating the squid not as meat to be frozen, but as structure to be preserved. This approach poses a deeper question. If beef marbling is engineered through genetic lineage and fat control, why don't we engineer squid texture through thermal tempo? After all, muscle behavior is a function of biochemical timing. What we call freshness is, in fact, a slow and deliberate deceleration of decay. If cold becomes not a punishment but a choreography, then perhaps the future of seafood logistics lies not in refrigeration technology, but in thermal behavior design. Transporting squid at this level means thinking in gradients, not in targets. It means designing thermal environments with the same sensitivity used in neonatal medicine or pharmaceutical transit. In the world of mass food logistics, that sounds excessive, but for squid, with its unstable enzymes, fragile fibers, and chemical volatility, there is no other way. Every cooling curve is a negotiation with entropy. Every shipment, a calibrated descent into stasis, not a plunge into ice. Cold alone cannot save it, but cold, precisely applied, can give it time. And in squid logistics, time is not a number. It is a boundary between form and failure. Transporting a giant squid is not about moving a product. It's about adapting to a material that behaves like no other. Traditional seafood logistics are built around rigidity. Crates, cooling systems, shock absorbers, all designed for animals with bones, defined shapes, and measurable structural resistance. Squid ignore these assumptions. They are fluid in form, fragile under pressure, and biologically unstable. Their behavior under stress forces a new logic, one that doesn't treat them as meat, but as dynamic systems. Unlike tuna, which tolerate abrupt movement and cold shock, squid suffer internal collapse from even mild forces. Handling them requires sensitivity more common in fruit logistics than fishery. In fact, some Japanese systems have borrowed techniques used in transporting ripe peaches, where the goal is to limit internal bruising from invisible vibrations. The result is a new transport philosophy, one that considers not only what the cargo weighs, but how it behaves under time, motion, and temperature. The breakthrough came with modular suspension containers, sealed, buoyant systems originally developed to move live jellyfish. These aren't boxes. They are controlled environments, simulating gentle ocean movement inside insulated tanks. Originally used for luxury exports like ornamental jellyfish to Dubai, these systems have now been adapted to squid. They reduce pressure points, dampen acceleration, and stabilize temperature with millimetric precision. What emerges is more than an engineering solution. It's a conceptual shift. Cold is no longer just a barrier against spoilage. It's a variable to be managed gradually. Acceleration is no longer a logistical detail. It's a structural threat. Squid logistics force the industry to think in terms of flow, not force, of response, not resistance. And this shift echoes beyond Squid. It opens a path toward adaptive logistics, where cargo behavior defines the vehicle, not the other way around. Japan's seafood sector is quietly leading this transformation, not through spectacle, but through precision, not by overpowering biology, but by listening to it. In the end, transporting squid is not a battle against time or distance. It's a dialogue with fragility, a demonstration that in modern agriculture and logistics, intelligence lies in restraint, and that moving something soft, unstable, and unpredictable without damaging it may be the highest expression of control. Did you imagine it took this much strategy to transport a squid? Comment 1 if this changes the way you see seafood logistics.